Welcome to the Crazy Hat Chemist. So another video on intermolecular forces. Bam! Okay, so how to determine the type of intermolecular forces or interactions that are occurring. So first thing, you're going to draw the Lewis dot structure. Hopefully you remember how to do that. Okay, so I'm going to have on the right and the left hand side of this slide two different things here. Okay, and then we have this right in the middle. So I'm going to write this down here with this blue line, and this is increasing intermolecular forces. So if you have an induced interaction, that is low intermolecular forces. It's a low boiling point and it's a low molar mass. As you increase in molar mass, you're going to have increasing intermolecular forces and consequently a higher boiling point. If you go from induced forces to a dipole-dipole interaction, something with permanent polarity, permanent dipoles, then you have increasing higher boiling point as well. And if you have hydrogen bonds, then you're going to even have higher boiling points. So let's see if we can apply this information and apply it to a few different molecules. Remember, you're going to draw the Lewis dot structure first. Which one has a really high boiling point, which one has a low boiling point. You're going to look at the molar mass. You're going to look at the type of intermolecular forces that are occurring. Okay, so let's give this a try. So I got water. So the first thing that we're going to do is we're going to draw the Lewis dot structure for water. And here's the Lewis dot structure for water. We have done this in a previous video. Okay, you should understand that there are a number of different intermolecular forces of which are occurring in water. Okay, and the strongest intermolecular force is hydrogen bonds. Then below that are dipole-dipole interactions because water is polar. It has a permanent dipole in it. Then, of course, because water does have electrons, there are London dispersion forces. I want you to see how I've written these words, though. The London dispersion forces are very, very small, so it's a small contributor to all the properties of water, the high boiling point, etc. And then the dipole-dipole interactions are contributing more than the London dispersion forces. And more than the dipole-dipole interactions are the hydrogen bonds, because the hydrogen bonds are quite extensive and quite strong in water, and that's why water has such high boiling point, high heat of vaporization, etc. We've gone over that already in a previous video. Let's take a look at another one. This is sulfur dioxide. So again, what you have to do is draw the Lewis dot structure. Here's the Lewis dot structure for sulfur dioxide. There's a lone pair of electrons on that central sulfur, and therefore that makes this sulfur asymmetric. It's a bent-like structure. So since it's bent, then we know the highest kind of intermolecular force. Well, it certainly does not have hydrogen bonds in it, but it does have dipole-dipole interactions. And of course, because it has electrons, it has London dispersion forces. So right here on the screen right here, the largest intermolecular force is a dipole-dipole interaction, and then a London dispersion force is smaller than that. Okay? All right, let's give another one a try. This is iodine. So we're going to draw the Lewis dot structure for iodine right here. So does it have hydrogens? No. Can it form hydrogen bonds? No. Okay? Is it an asymmetric molecule? Is it polar? The answer is no. So it cannot have dipole-dipole interactions because it does not have a permanent dipole in the structure. So the largest contributing force here is a London dispersion force. Again, this is why iodine is solid, because it has such a large molar mass and can can have induced dipoles that will occur. Okay, let's take a look at another one. And this is CH4, which is methane. You're going to draw the Lewis dot structure of this. Okay, now, does methane have hydrogens? Yes, it does. Now, can these hydrogens form hydrogen bonds? The answer is no. Any carbon-hydrogen bond cannot form. This is almost a pure covalent bond. The electronegativity of carbon is 2.5. The electronegativity value of hydrogen is 2.1. The difference between those two is so very small that it is effectively a very slightly polar, if not more covalent in character of this bond. Because this is not a very large difference in electronegativity like oxygen and hydrogen in water, That is a very strongly polar covalent bond in water. But in methane, the carbon-hydrogen bond is strongly covalent. Therefore, this cannot form hydrogen bonds even though it does have hydrogens in it. Okay? Is it an asymmetric molecule? Does it have a permanent dipole? The answer is no. So therefore, there are no dipole-dipole interactions. Does it have electrons? Well, of course it does. Everything that we work with in chemistry pretty much has electrons, so the largest contributing factor are London dispersion forces. Now, I want to delineate something here. Iodine has a very large molar mass in compared to methane. So iodine can have induced interactions like I've discussed in a previous video. This is why iodine is a solid. Okay? Whereas methane is relatively spherical in addition to the sphericalness of iodine, but methane, CH4, it has a very low molar mass. And that low molar mass does not allow that electron cloud to become polarized. And that's why methane is a gas at room temperature and pressure. Okay? Hopefully all those worked well for you. Okay? I am the Crazy Hat Chemist, and of course, I got myself a crazy hat going on. Well, this will keep my ears warm. Okay, give me a thumbs up if you like that video. Subscribe to my YouTube channel, and yeah, tie this stuff in a knot. Okay? Have a good day. See you later. Bye now.